Hello once again, class, and welcome to another mock lecture. Today we're going to be discussing tree diagrams. Now, in the last video where we were talking about an intro to probability and we defined what a sample space was, and we went through these two sample spaces, sample space of rolling two dice where we set up a 6x6 array to find all 36 outcomes, and the sample space of flipping three coins, where we found that there's 8 possible outcomes because each coin can be either heads or tails. Today we're going to be discussing a more structured approach to coming up with these sample spaces. And one way that you can do that is with a tree diagram. So I'm going to go over the sample space of flipping three coins utilizing a tree diagram. And here it is. Here's a tree diagram. Each kind of stage of this thing, each tier, I guess you could call it, of the tree represents a new coin that's being flipped. And, I organized this one horizontally like this, where, we're first flipping the first coin and it can only be heads or tails, and then that branches off into some other stuff that can happen. But you can arrange these things vertically as well. It doesn't really matter. Trees can be oriented in whatever way you'd like them to be. But let's go with horizontal and I'll kind of explain this. So the first coin, right, that's being flipped, right, coin 1 can either be heads or tails. Based off of whatever it is, right, you flip the next coin. And so then now we're in this tier here. And let's just say that the first coin was tails. Well, then the second coin can also be heads or tails, right? And let's say that it ends up being heads. So then we go to the third stage, and that can either be heads or tails. And so what you do is you end up kind of creating, and let's say it's tails. You end up creating this kind of pathway, and that is an outcome, right? That represents an outcome. Okay, in this one I highlighted the heads one. But that's this one right here. Tails, heads, heads. Right, here's another outcome. Heads, tails, heads. So following each path, here's tails, tails, tails. Following each path gives us each of these things. And there are indeed 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. That's why we have 8 outcomes that are listed here. Now, when you're talking about a tree diagram, specifically for coming up with sample spaces, what you're doing is you're kind of presupposing that all of the outcomes here are equally likely outcomes. And so if I wanted to ask the question, what is the probability of rolling all tails? Well, that's just one of 8 different paths. So the probability would be 0.125. It'd be 1/8. In a later video, we are going to talk about probability trees, which are kind of specialized tree diagrams. But we'll have a separate video on that, and each outcome in those are not actually equally likely. But when you're setting up a sample space like this, we're kind of presupposing that all of the outcomes are equally likely. So let's look at some more examples of setting up some sample spaces and even asking some questions about probability. All right, example number 1. Suppose a bag contains 4 marbles, where 2 of them are red, 1 is blue, and 1 of them is yellow. If we draw 3 marbles, what is the probability that both of the red marbles are going to be drawn? So the first thing we need to do is we need to figure out what are all the possible outcomes. Okay, what is every outcome that could happen when we draw 3 marbles? We're going to be drawing them in a specific order. So in this example, order does matter. We're not really going to get into permutations and combinations in Math 105, but where it's applicable for any of us that are coming from a background that knows what permutations and combinations are. Here we are talking about permutations. In any case, we need to come up with a sample space for this. So on the first draw, there are 4 marbles that you could pick. You could draw the first red one, the second red one, the blue marble, or the yellow marble, right? There's 4 marbles in the bag, so you have a 1 in 4th chance of drawing any of these things. And again, for this example, this particular red marble, maybe you want to call it red 1 and red 2, right? They're different marbles, so they count as a different outcome. Okay, so that's the first draw. In the second draw, and I'm just going to go kind of one at a time here. In the second draw, where you pick red 1 first, red 2 marble is still in there, right? So you can still draw a red, or you can draw the blue, or you can draw the yellow marble. And in fact, that same kind of tree subtree exists for red 2, right? But instead here, this is red 1 is still in the bag, and so it can still be drawn. But then the blue marble's there, and the yellow marble's there. For blue and yellow, both red 1 and red 2 are available. They're still in the bag, and then when you draw blue first, yellow's still there, or when you draw yellow first, blue is still there. So again, Remember what we're doing is we're listing all of the possible outcomes that can potentially happen, and this is on the second draw, but we have to base it off of what was drawn first. Okay, then we go down another tier, right? So the height of this tree is 3, I guess in this case, because there's 3 rounds of things that are happening. But if you draw the red 1 marble first, followed by the red 2 marble, and I'm following this path here, red 1 first, red 2, well then you can either draw the blue or the yellow marble, and that's it. Whereas if you draw the red 1 marble first, then the blue one, well, red 2 is still there, or the yellow one, right? Red marble first, then the yellow, well then you have red 1, or red 2 rather, and also the blue marble. Right, and that same idea can be talked about for this subtree, except in this subtree, red 1 and red 2's position are switched. Okay, so that explains that first half of this tier. The second half goes about as you'd expect, right? So here in this case, if this is red 1, then this must be red 2. If this is red 2, then this must be red 1. I didn't label them all because I didn't want to make them super confusing. Just to show you where a red marble shows up is really the main point here. Notice that in these branches, right, this to this, and this, excuse my non-straight lines, to this, if you draw a blue and then a yellow, or a yellow and then a blue, then both the red marbles are remaining. And you're only going to draw one of them, so that actually wouldn't satisfy the probability that we're kind of looking at here. But that's the whole tree diagram. That is the sample space. And so what I like to do is I like to list out, well, here are all the possible outcomes. Red first, red second, blue last. Red first, red second, yellow last. Red first, blue second, red last. So on and so forth. There's 24 of them. When you count them all up, there's 24 of them. Well, of those 24, 12 of them have both the red marbles in it. So remember that when you're looking at a probability, and here we're looking at the probability that both red marbles are drawn. I just abbreviated with both red, which actually is kind of confusing because we're drawing 3 marbles. So really what this should say is the probability that both red marbles are drawn in 3 draws. But that's the way I don't want to write all that. So just pretend that it says that there. But in general, a probability is the number of desired outcomes, right? The number of times the outcome we care about shows up in the sample space divided by the total number of possible outcomes. Because remember, each of these things is an equally likely chance of happening. That's why we're able to just get away with just counting all of these and then dividing it by the total number of outcomes. So we get 12 over 24, which is just 0.5. The probability that both red marbles are drawn in 3 draws is 0.5, or 1/2. Or you could translate that to being there is a 50% chance that you draw both red marbles when you draw 3 marbles from a bag of 4. Right, with this specific makeup. Example number 2. Suppose that we flip a coin and then we roll a 4-sided dice. Find the probability of flipping heads and rolling an even number. Okay, so again, what I want to do is I want to figure out what is the sample space for this. If we say that we flip the coin first and then roll the dice, then when we're drawing our tree diagram, we would start off with just having 2 possibilities. You flip the coin, you either get heads or you get tails. But then based off of that, you roll a dice, and there would then be 4 branches emanating away from each of these things for all the possible outcomes for the dice roll. It's the branch that gets you to the very end of the tree that tells you what that outcome is. So like the one I just highlighted, that's H1, right? Here's another one. From go to H, go to 3, that's H3, right? And so here they all are. H1, H2, H3, H4. T1, T2, T3, and T4. We care about what the probability of flipping heads is, so we're just going to be focusing on this subtree over here, but then you have to roll an even number, and that's just these 2 paths. H2 and H4 are only 2 of 8 possible outcomes, and so the probability would then be 2 divided by 8, or 1/4, or 0.25. Example number 3 is a little bit tricky, but it says, suppose 4 people are randomly assigned to 2 teams. What is the probability that the oldest and youngest are on the same team? So yeah, I guess we're kind of assuming that everybody has a different age of these 4 people, and there is an oldest person and there is a youngest person. But the way that I tackled this is when I was setting up the tree diagram, I made it have a height of 4. So it's 4 tiers deep. I guess is another way to put that. And what I'm doing is I'm saying the first person can either be assigned to Team A or Team B. And then based on that, the second person can either be assigned to Team A or Team B, right? Or maybe on this side, Team A and Team B. So the second choice looks very, similar in that regard. But now you have to start paying attention to what the context really is what you have to start paying attention to in this particular problem. If we follow this branch, we've assigned the first person to Team A and the second person to Team A. And so the other two people are automatically going to be in Team B. So what we see is this behavior, right? We automatically, and I probably should even go to the fourth person there on the height of this tree diagram, because the fourth person is also going to have to be in B. But if we follow this path, A and then B, well, then the third person can still be either on Team A or Team B. So you have to pay attention to the context as well as what's happening at each tier or at each level of the tree diagram so that you know what the structure is going to look like. Okay, and then the same thing happens over here. If we follow this branch, we go first person gets assigned to Team B, second person gets assigned to Team B. Now the third and fourth person are automatically guaranteed to be in Team A. So the rest of the tree then looks like this, because now at this point, if you go here to go first person's A, second person's B, third person's A, well then the fourth person is automatically chosen for us. So really there's no choice after the third person. The fourth person is just automatically pigeonholed into whatever whichever group is missing a member, they automatically get put into. All right, so we set up the tree diagram. I want to write the outcomes down here, but I don't have a lot of room, so I'm going to rotate this thing this direction so that I can write out all the outcomes, right? There's 6 of them. There's 6 different outcomes for assigning teams, right? There's 6 possible teams, I guess you could say. 6 different organizations of teams. 6 different pairs of teams. That's the one. Now, we're trying to figure out the probability that the oldest and the youngest person are on the same team. So let's just assume, without loss of generality, because I could do this for any 2 numbers that I want, but let's just assume the first and the second person are the youngest and oldest respectively. So then what I'm doing is I'm looking for, well, where is the first choice and the second choice the same letter, because then they'd be on the same team, and that happens in the first outcome and also the last outcome. And so my probability of old and young being on the same team would just be 2, because there's 2 teams. There's 2 outcomes where the first and second person are on the same team out of 6 total, so you get 1/3. Now, you might be saying, well, but that's if you do first and second. What if you did like first, so let's do first and third. Okay, let's do that, right? Now we don't care about the ones that I've highlighted here. Whoops. What we care about is where the first and third letter are the same. So like here's one, first and third, and here's another one, right? First and third. Well, that's still the same probability. That's still 2 out of 6 of them. There's no other places where the first and third are going to be the same. So that's what I mean with without loss of generality. Means let's just assume, because it doesn't matter anyway, let's just assume 2 of the numbers are the youngest and oldest respectively, and I just happen to pick 1 and 2 for this example. But you can pick any 2 numbers you want to be the oldest and youngest. 2 numbers are the youngest and oldest respectively, and I just happen to choose the first and the second. That was a long rant about that, but hopefully that makes sense. That's it. Okay, really this one's just about what is a tree diagram. And as long as you're walking away from this video knowing that a tree diagram has some structure to it, where you have choices based on previous choices and it creates this kind of tree structure, and that also it helps you figure out some sample spaces, then I think that that's good enough. If you guys have any questions, please don't hesitate to leave a comment below or shoot me an email. Thanks a ton for watching, and I'll see you in the next one.